Ladies and gentlemen, welcome back to one more edition of Projectile Motion. We've spent the last two lessons on horizontal launch, and this time we're going to consider angled launch. We're not going to get as mathematical with angled launch. It involves trigonometry at a level that we're not covering in this class. Okay, with a little more time we could certainly cover it, and we've covered it in years past, but this lesson is going to focus just on the general behavior of a projectile that's launched at an angle. In other words, we're not going to really do any mathematical problem solving, but we are going to cover how the projectile moves and how its various velocity, acceleration, and displacements change in the trajectory. So let's get right to it. On the screen you see an example of a projectile launched at an angle, right? For example, a bat hitting a baseball into the outfield, or the outfielder throwing the baseball back. Okay, typically these are examples of projectiles launched at an angle. Let's look at how the velocity of the projectile, okay, I want to call it a baseball in this problem, how the velocity of the baseball changes as it rises, reaches its apex, right, another word for the top of the path, and then falls back down. And we're going to use our same approach as before. We're going to look at this 2D motion as a combination of two 1D motions, right? We're going to look at the horizontal velocity and displacement, and we're going to look at the vertical velocity and displacement. I'm going to keep the same color coding as I have previously, okay? What I'm going to do is I'm going to represent the starting velocity, okay, the velocity with which the baseball was hit, as these two arrows here, all right, like so, okay? And remember that the total velocity, okay, is going to be a combination of those two, right? The Pythagorean theorem combination, okay, and we'll use a red arrow for that. In other words, at the beginning, it's going something like that, okay? Now, as the ball rises, I want you to consider how the velocity changes. Remember that in projectile motion, there is still no horizontal acceleration. That means that sometime later, right, when we come up here, notice that I have the same size green arrow to represent the same amount of horizontal velocity that hasn't changed. However, you'll see in this problem that because of gravity, right, the vertical velocity is changing, okay? It's a smaller arrow. And at some later time, right, we could even put another one right here before we get to the top. The horizontal velocity still hasn't changed, but the vertical velocity is even less. And then when we get to the top, notice what happens momentarily. The velocity of the projectile in the vertical direction is 0. In other words, it's stopped rising, right? So one split second at the top, the angled launch projectile is traveling only horizontally, okay? But then just a split second later, all right, we are going to see basically the opposite effect. Before we continue, we should maybe sketch in the total velocity as well with the red arrow. Okay, in other words, because the vertical velocity is decreasing, therefore the total velocity is decreasing. Okay. Also notice that the angle of the total velocity is getting flatter. Right, it went from steep to flatter, and then at the apex, it's actually momentarily 0 degrees, right, totally to the right. And now let's watch what happens as the baseball starts to fall. Okay, you're going to see here that there's a nice symmetry to the motion. Okay, in other words, things behave on the way down exactly as they do on the way up, just with the direction inverted. So notice that the horizontal velocity remains the same, still using the same size green arrow. Okay, but of course now the vertical velocity is flipped, right? It's negative. It's in the negative direction. Okay, so like that. And then finally, when I return to the same height that I started at, okay, I actually have the same velocities that I did at the start. Okay, in other words, the ball hits the ground with the same total speed as it left the baseball bat. Okay, so again, we could draw the red arrows, okay, to represent the total velocity, and now notice that the total velocity is growing, right? The vertical velocity is getting larger, therefore the total velocity is getting larger, and boom, down there you can see that that arrow is about the same length as the arrow at the beginning. Okay, In other words, that's a symmetry, right? It's at the same location, has the same velocity, it's just going down instead of up. Okay, let's move on to another screen. There's some more cool things about projectile motion, okay, and that has to do with the range of the projectile. And this is something you may have thought about when you built your launchers, okay? But a good question to ask is, assuming that you're throwing as hard as you can throw, you're hitting as hard as you can hit, what would be the best angle at which to hit a baseball to get it to go as far as possible, okay? If you think about it, I think you'll realize that if you hit it too flat, right, let's use something like this right here. If you hit it too flat, oops, it'll be in the free form. If you hit it too flat, I won't spend a lot of time in the air, right? I won't spend a lot of time in the air. It might go like that, okay? If you hit it too high, right, it'll spend a lot of time in the air, but it won't really, that's an ugly parabola, it won't really accomplish what we want, which is to get as far away as possible, okay? In fact, there's a point there where I can get it to go the same distance, whether I hit it really flat or really angled. Okay, so you don't want to hit it too flat, it's not enough time in the air. You don't want to hit it too high, that's just a bunch of height and not a lot of range. As you might have guessed, okay, the max range is going to be sort of a balance between height and horizontal, and that's going to be the 45 degree. Okay, in other words, you're going to get the maximum range when you're at 45 degrees. Okay, but there's something else even cooler here, okay, and that is that you can aim at two different angles and get the same range. Okay, in other words, this here might just be at 20 degrees. Okay, but at its complement, right, 90 minus 20 degrees, okay, which would be this one here. If you launch this one at 70 degrees, you get the same range. Okay, another way to say that is complementary launch angles have the same range. Okay, maybe just for kicks, we could put one more in here. Okay, let's color it something different. Maybe something like this. Okay, and let's see, that would be maybe, that's less than 45, right? So maybe 30. Okay, and then 60 would look like that, maybe. Okay, so that we have this as 60 degrees and this as 30 degrees. Complementary launch angles yield the same horizontal range. Okay, the last part of our lesson is to show you a few more interesting things about angled launch. All right, I'm going to switch screens one more time. Okay, and before I discuss the example which you see on the screen, which is that of a cannonball being shot out of a cannon, I want to review briefly what you already know about 1D kinematics. Okay, and I've kind of scrunched that into the upper right corner. If you drop a ball from rest, okay, its initial velocity is 0, right? So if we look at our equation 3 here, okay, from the board, which I've reproduced, and assuming that this is the origin, right, then this is 0, and this is 0, and we're just left with this sort of simplified version of equation 3. If you drop an object from rest, okay, you'll see that after 1 second, okay, I'm going to round here and make acceleration due to gravity, okay, make that about 10, okay, instead of 9.8, just to round these off. Well, it turns out that in 1 second, a vertically falling object falls 5 meters, okay, and after 2 seconds, it will have fallen 20 meters, okay, and after 3 seconds, it will have fallen 45 meters. These are just numbers that I got from equation 3, plugging in t equals 1, t equals 2, t equals 3. And you've actually worked these numbers out before, okay? Now, here's the cool thing. Watch what happens here. If we go over to this cannonball scenario, it turns out that a projectile launched at an angle actually has a very similar behavior, okay? This straight line represents, okay, the way that the cannonball would move if there were no gravity, right? It would just fly into space. There'd be nothing pulling it to Earth, okay? But because it's being pulled to Earth, okay, and remember, gravity from our demonstration apparatus, the projectile motion where we shot a marble and we dropped a marble, we learned from that gravity doesn't really seem to see horizontal motion. I'll give you one guess here how far do you think this distance is between the no gravity straight line and the projectile motion line, which is due to gravity? You guessed it, 5 meters. Okay, it's 5 meters off that line, just like a freely falling object falls 5 meters in the first second. Okay, this distance after 2 seconds, right? The discrepancy will be again 20 meters, right? Exactly the same as for an object dropped from rest. In other words, once again, you see another example of gravity not really seeing the horizontal motion, right? It treats all projectiles exactly the same in the vertical direction. This concept is commonly applied to an example you see I just scratched in on the bottom. Okay, we've got a gun, and you're the cruel type, so you're trying to shoot at a monkey that's in a tree. Okay, don't ask me why, but this is a common demo, right? The monkey and the hunter. Okay, and the question is, if this monkey is just going to drop out of the tree, do you aim at the monkey, right? Do you aim at the monkey in order to hit him, like that? Or do you aim below the monkey in order to anticipate the monkey's fall, and you try to basically intercept the monkey as the monkey falls to the ground? I will let you think about the answer to that. The answer is in the 2D kinematics notes. Of course, you can Google it, or we will discuss it in class next time.